the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who are currently going through vector spaces and null spaces, column spaces, and linear independence of vectors from within those spaces. We are now shifting our attention to a very important topic within vector spaces, which is called bases, or some people will call it bases, but I call it bases. That will be the plural of the word basis. Now, if you didn't watch my last video, I just want to draw your attention to the very first concept I mentioned in that video, which is we're now asking the question, what is the set of vectors that span a given vector space most efficiently? That's actually what we're building in this video. That's called a basis for that vector space. But what is a basis? Well, let H be a subspace of a vector space V. An indexed set of vectors B1 through BP in V is called a basis for that subspace if the following two conditions are met. That set of vectors is linearly independent, and the span of those vectors is equal to that subspace. So again, we're talking about a subspace H here. And we're saying we have some building blocks for this subspace H, which is a subspace of the vector space V. And we can think of a basis as like the primary colors, like red, green, blue, right? Those are our primary colors. And in fact, you have a larger palette of colors. You have larger amounts of primary colors if you want, but you really want to reduce your space down to the most primary vectors that can build everything or generate everything in your subspace. If you can find that very small collection of vectors that builds all vectors in your subspace, then you have the basis for your subspace. Remember, it has to build all of your subspace, so that collection of vectors had better span your subspace, but you also want to make sure that there's not redundancy within that set of vectors. Therefore, that set of vectors must be linearly independent. Finally, before we leave this page, I want to mention that when I say basis, I will often trade out that word for the phrase generating set, because you're generating your entire space. I just have a habit of saying that. And actually, really, we do use that word generate every once in a while in mathematics. So if I don't say basis, but instead say our generating set is this, it means the same thing in my opinion as a basis. All right, we should probably look at some examples to really get a good footing here. This very first example is not one that we need to work through, it's just one that we need to recognize. The columns of the identity matrix I sub n form the standard basis for Rn. So for example, in R cubed, the columns of the identity matrix, the 3x3 identity matrix, forms the standard basis for R cubed. Now, I don't want you to think that this is the only basis for R cubed. This is just what we would call the standard basis. It's the most obvious basis. For example, if you wanted to generate the vector in R cubed, let's just pretend -3, 1, 8, that can be written as a linear combination of the columns of the identity matrix as follows. The reason why we like the identity matrix, or basically the standard bases for Rn, is that it makes writing vectors in terms of those basis vectors easy. We know that we would go over a -3 units in the x sub 1 direction, we'd go over 1 unit in the x sub 2 direction, and we would go over 8 units in the x sub 3 direction to arrive at this vector right here. Very, very easy to understand. However, these vectors are not the only vectors that form a basis for R cubed. I want to note a couple things here. First off, these three vectors here form a linearly independent set. Remember, if you have a set of vectors that is linearly independent, and if the span of those vectors forms your subspace, which our subspace is R cubed, then you have a basis for your subspace. And if you're wondering why I'm calling R cubed a subspace, it's because of the way the definition of the basis was formed. We're talking about a basis for a subspace of a vector space. But remember, subspaces are vector spaces, and they are subspaces of themselves. So I can simultaneously call R cubed a subspace of the vector space R cubed. But again, the two conditions to be a basis are linear independence of our vectors and the fact that our vectors will span our space R cubed. You can actually knock both of those conditions out really quickly. If you form a matrix, let's just form a matrix A. In fact, we know it's the identity matrix, but let's just call it the matrix A for this example because that's usually what you're going to call it anyway. We'll form a matrix with those column vectors as the columns of our matrix. Notice each column has a pivot. Notice this matrix is square. Thus, by the invertible matrix theorem, if you have a square matrix and, scrolling down, if your matrix has a pivot in every row, or in other words, in every column, then everything in the invertible matrix theorem holds. All of that central column there holds. Specifically, the columns of our matrix will span Rn. Our matrix is an n by n, in this case 3 by 3, so the columns will span R cubed. So we have knocked two things out at once. Not only that, but if you scroll down a little bit, the columns of A should also be linearly independent. So we have in one fell swoop shown that the columns span R cubed and they're linearly independent, just using the invertible matrix theorem. So formalizing that here, A has a pivot in each column implies the columns of A are linearly independent and the columns of A span R cubed. And by the way, that was by the invertible matrix theorem. This is something you're going to have to do every time that you claim you have a basis for a space. Now, as I said, there are other bases for R cubed. You don't need it to be the standard basis. So let's do yet another example in R cubed. Show that the following vectors form a basis for R cubed using two different approaches. Now remember, a basis just requires your set of vectors to be linearly independent and they need to span R cubed. The easiest approach is to build a matrix with those columns and find out if the determinant is non-zero. So that's the first approach I'm going to use. So I let A be that matrix right there, the matrix where its columns are the column vectors here. Now what I'm going to do is either perform some row operations or just straight take the determinant. I'm actually just going to straight take the determinant and I'm going to expand about the second column. Let's go ahead and do this. And we get down here, as long as my math is correct, pretty okay. I think that's all right. Right, so we have negative 15 minus 4 times a negative 4. I actually don't bother even computing it. I just know it's not 0. As long as the determinant's not 0, that will imply that the columns of A are linearly independent and span R cubed by the invertible matrix theorem, which implies the columns of A form a basis for R cubed. That is honestly the easiest approach. But I did ask you to use two different methods to show that these vectors form a basis for R cubed. So another way that you can do this is more rudimentary. It's using older methods. Well, if you want to show these vectors are linearly independent, you want the only solution to this vector equation to be the zero solution, right? The trivial solution. So you can place these column vectors in an augmented matrix with the zero vector, and then row reduce. Notice our resulting matrix system, or our resulting augmented matrix, has a pivot in each column. Therefore, there are no free variables, which implies the homogeneous equation AX equals 0 only has a trivial solution, which means that this vector equation only has a trivial solution, which means the columns are linearly independent. Moreover, you could see that we have 3 pivots in this augmented matrix. We have a pivot in each row, which means the columns span R cubed. So the columns are linearly independent, they span R cubed, that implies they form a basis for R cubed. Now, if you look at those two approaches, while I shortened up the ink on approach number 2, it should still feel like it was a much more cumbersome approach. We used antiquated techniques in approach number 2. When I say antiquated, I really mean like techniques from chapter 1 of your linear algebra text, something like that. But we used really modified or modern techniques for approach number 1, specifically the invertible matrix theorem. And it was super easy. The only problem is, if you cannot form a matrix to begin with, the invertible matrix theorem is out. But if you can use it, this example should showcase you should use it. Find out if the determinant is 0. If it's not 0, then you have found a basis for your space. Let's take a look at another example. In this example, we cannot, at least as of right now, we cannot form a matrix from these vectors, at least right now. We will be able to eventually once we learn about coordinate systems, but for right now, let's just keep it as if we don't know that. So S is this set of vectors, 1, 1 plus x, and the quantity 1 plus x being squared. We want to show that S is a basis for the vector space P sub 2. Remember, P sub 2 is a set of polynomials of degree at most 2. Now, before I even begin, I just want to mention this will be a basis for P sub 2. We're just going to show it, but it will be a basis, but it is technically not the standard basis for P sub 2. I'll write down the standard basis in a little bit. For right now, we're just going to focus on this set of vectors specifically. We'll start with the claim that we're letting V sub 1 be 1, V sub 2 be 1 plus x, and V sub 3 equal 1 plus x quantity squared. Now, I said it in the last video, but it bears repeating here. When you're working with structures from linear algebra, you have to be very rigorous. But the moment you step into any prerequisite material, there are pretty much a ton of things you can assume because you've already worked with that material for many, many years. For example, we happen to know that V sub 3 can be expanded out, 1 plus 2x plus x squared. The second thing that's kind of important, and this is actually really important to know from our prerequisite material, is that V sub 1, which is 1, and now I'm just going to consider it to be the number 1 for now, that 1 cannot be generated from any linear combination of V sub 2 and V sub 3. And note how I wrote this, because I really want to just stay within my prerequisite algebra material for now. I'm saying 1 cannot be generated via any combination of 1 plus x, and this is technically 1 plus x being squared, but I multiplied it out. Think about that. That just totally makes sense. Anytime you have any non-zero multiple of this polynomial, you will have an x squared. And there's nothing in this to kill off that x squared. So any linear combination where the coefficient of this guy right here is non-zero will result in an x squared. But we don't have an x squared. So that means the coefficient of this has to be 0. But now to get this to turn into 1 is pretty much impossible. Not just pretty much, it is impossible, because no matter what scalar I park in front of 1 plus x, unless that scalar is 0, the result will always have an x involved, and there's no way to rectify that with only needing a 1 on the other side. The same argument holds for V sub 2 and V sub 3. V sub 2 cannot be created from any linear combination of V1 and V3. It's just not possible. And finally, V3 cannot be created from any linear combination of V1 and V2. I'm not going to bother writing that down, but you could easily see it, right? Any multiple of V1 and V2 added up will never give you an x squared term. So that's out of the realm of possibility to create a linear combination of V1 and V2 becoming V3. It just can't happen. So because of those three, which I'm not writing the V sub 3 one here, but because of those three conditions, the set V1, V2, V3 is linearly independent. Now, a lot of students will look at this and say, well, that just doesn't seem rigorous enough because we've gone through so much rigor, and now you land us in an area where you're kind of hand waving a little bit. I'm not hand waving. You could actually set up a linear combination of these three vectors, set it equal to 0, and do what's called comparison of coefficients. So what I did is I distributed everything out, and then I collected like powers of x. For example, all the constants I collected together. I have one C1, one C2, and one C3. So I grouped those up as a single constant. Then I looked at all the multiples on x. We had one C2 of x, we had two C3s on x, and then finally I had C3 of these x squareds. Now, using comparison of coefficients, on the right hand side, the coefficient of x to the 0th, or in other words the scalar, is 0. On the left hand side, it's C1 plus C2 plus C3. As far as coefficients on x to the first, on the left hand side we have C sub 2 plus 2C sub 3. On the right hand side we don't have a coefficient of x. And then for coefficients of x squared, on the left hand side we have C3 as the coefficient of x squared. On the right hand side we don't have an x squared. And this tells us C3 is equal to 0. Solving the second equation by back substitution, you'll get that C2 is also equal to 0. And inserting those into the first equation, that tells us C1 is equal to 0. That would be a more mathematical way of going about it versus a more conceptual way of going about it. But here you go. The only linear combination of those three vectors that will lead to 0 is if the weights are all 0. Therefore, these vectors are linearly independent by definition. So two ways to tackle that. Again, we can't use matrices here, not yet. Now, to show that these vectors span P sub 2, we're going to go ahead and let W be a vector in P sub 2. That is, we have a polynomial of degree at most 2 from P sub 2, and we want to represent that polynomial somehow as a linear combination of these vectors. So suppose the vector W is just this quadratic right here. Again, the coefficients could be 0. So a sub 2, a sub 1, and a sub 0 could all be 0, or one of them could be 0, or two of them, doesn't really matter, or none of them. That way we have all different possibilities. It could be a second degree polynomial, a first degree polynomial, or a 0th degree polynomial. Now there are a lot of ways you could do this. And because this is a video, I suppose I should do the one that you're going to perform the most often. However, I want to show you a very cool way when we're done. Now the first way I'm going to show you, which is kind of the more mechanical way, but doesn't involve some creativity. So the first way I'm going to show you is basically what we did here. I'm just going to grab a linear combination of my three vectors, 1, 1 plus x, and 1 plus x quantity squared, and I'm going to set it equal to that vector W, and I'm going to see what are the conditions that will generate that vector W. Can it be generated, basically, is what I'm asking. So is there a solution really to that equation? Now we've already modified that left-hand side to look like this. So I'm going to go ahead and just grab this modified version right here, and I'm going to rewrite the left-hand side of this equation as that. Great. Now I'm going to go back and use comparison of coefficients. For the constant terms, on the left-hand side, we have C1 plus C2 plus C3. On the right-hand side, we have A sub 0. For the coefficients of x to the first, on the left-hand side, we have C2 plus 2C sub 3. On the right-hand side, we have A sub 1. And finally, for the coefficients of the x squared term, on the left-hand side, we have C sub 3. On the right-hand side, we have A sub 2. So is there a solution, a combination of C1, C2, C3, that will yield this vector right here, this arbitrary vector in P sub 2? Well, I know one thing for certain. C sub 3 has to equal A sub 2, which will imply C sub 2 is equal to A1 minus 2 A2. And that will imply that C sub 1 is equal to A naught, and I will subtract C sub 2 from both sides. That's a negative A1 plus 2A sub 2. And then subtract C sub 3 from both sides, which is another loss of A sub 2. So C sub 1 should equal a naught minus a sub 1 plus a sub 2. So again, to answer the question, if I was given an arbitrary vector in our vector space p sub 2, can that be generated by a linear combination of the vectors that we were handed, 1, 1 plus x, and 1 plus x quantity squared? And the answer to that question is yes. No matter what vector we're handed, as long as we write that vector as a2x squared plus a1x plus a naught, then c3, the coefficient of 1 plus x quantity squared, should be a sub 2. C2, which is the coefficient of 1 plus x, should be a1 minus 2a sub 2. And then finally, c sub 1, which is the coefficient of 1, should be a naught minus a1 plus a2. That's a very mechanical way of doing it, but it does showcase that the span of those three vectors is p sub 2. It generates any vector in p sub 2. Now, off to the right-hand side, I'm going to show you a different way you could have done this, and we're going to start with this group right here. We're going to let w be in p sub 2, and we just want to know, can we generate that w from v sub 1, v sub 2, v sub 3? And the way we're going to do this is we're going to use our prerequisite Calc 2 material. This is a really good thing to pay attention to, because if you are taking this course before differential equations, you will need this review. If you're taking it with differential equations, you'll need this review. If you're taking it after differential equations, it's a cool technique, so watch it anyway. Recall that we had something called a Taylor polynomial expansion. Once I said that, by the way, half of you probably groaned, but we had a Taylor polynomial expansion way back in Calc 2. And the Taylor polynomial expansion said the following: if a function has a Taylor polynomial expansion, then the function can be written as the infinitely long polynomial where each term is the nth derivative of f evaluated at a, where we are centering our expansion, divided by n factorial times x minus your center a to the nth power. The neat thing about recentering polynomials, specifically this polynomial right here, is that there's only a finite number of terms to the infinitely long expansion. You start with your polynomial, and remember, we'll need to evaluate the polynomial at the new center. We're going to recenter this polynomial at, well, if you take a look at our vectors, they're all not at x, but instead at x minus a negative 1. That's vector v sub 3. V sub 2 is also centered at x minus a negative 1, and v sub 1 is a constant. That's centered anywhere. It doesn't really matter. So we're going to let a be a negative 1 in this expansion. So I have my function. I'm going to evaluate that function at our center. Now I'll take the derivative of our function, and I'll evaluate that derivative at the center. Finally, I'll take the next derivative of our function. And you can see why I said finally, because one more derivative beyond this and we have a 0. So from this point forward, all other derivatives are 0. And by the way, if you evaluate that derivative at the center, it's just 2a. So our polynomial, our original function, can be written as the 0th degree polynomial, which is just the polynomial, evaluated at a, and we've just written that out right here. The polynomial evaluated at the center is a sub 2 minus a sub 1 plus a sub 0, and that's all over 0 factorial times x minus our center to the 0th power, plus, moving on to the first derivative, evaluate the center divided by 1 factorial times this polynomial to the first power. Well, the first derivative evaluated at a, or at negative 1, is negative 2 a sub 2 plus a sub 1. Divide that by 1 factorial and multiply that by x minus the center to the first power. And finally, f double prime at the center divided by 2 factorial times x minus the center squared. If you clean this up, you'll get the following. Now I'm going to pause here to highlight some things. Notice the constant here is a sub 2 minus a sub 1 plus a sub 0. Oh, well that's interesting. The coefficient c1 that we knew would be in this linear combination, the coefficient of our constant term, it ends up being a sub 0, positive a sub 0, minus a sub 1 plus a sub 2. Well, that's interesting. How about the coefficient c sub 2, which is a coefficient of 1 plus x? Could we find that? Is there a coefficient c sub 2 that'll work? Well, what we found over here was that coefficient was going to be a1 minus 2a sub 2. Guess what it is here? a1 minus 2a sub 2. And finally, our coefficient c sub 3 of that quantity 1 plus x being squared, well, we found in our previous method that was going to be a sub 2. In this method, we found it's going to be a sub 2. So a really cool way to do it using your Calc 2 material, Taylor polynomial expansions. It's really nice. All you're doing is recentering this arbitrary polynomial at the obvious center they've handed us here. Now, this method would not really work very well if, for example, this was a 2 plus x, because then your center here is -1, the center there is different. So that's an issue. But the way they handed this to us is pretty obvious that we're centering at -1. Anyhow, in any case, we have shown that these vectors are linearly independent and that they span p sub 2. Thus, these vectors are a basis for p sub 2. Now, I did say in that warning up above, that's not the standard basis for p sub 2. Technically, the standard basis for p sub 2 is somewhat obvious to see, 1x squared. That would be the standard basis for p sub 2. But here we have a basis that is not the standard basis, but still a basis for p sub 2. So we arrive at the very last theorem in this video. It's called the spanning set theorem, and I've alluded to this already. I'm going to summarize it just with language here. We'll start by saying that we're working within a vector space and that we have a collection of vectors from that vector space. And we're going to let H be the span of those vectors. That's the important part we'll start with. So that's everything I've highlighted right there. And I've summarized it in language here. Let H be the subspace of V created from the span of those vectors. Now, I've mentioned it earlier in this video that if I want to create a basis for this subspace right there, which is H, which is created from the span of these vectors, I want the smallest number of vectors that still span the entire subspace H, but are also all linearly independent. So we're all going to shake our heads or nod our heads when I say the following. If there's an offending vector in here that is a linear combination of the other vectors in here, I can remove it from this set. Everybody nods their head and says, okay. So let's just say that V sub 2, or better yet, for argument's sake, let's just say V sub 1 is a linear combination of all the previous vectors. Well, if V sub 1 is a linear combination of those remaining vectors from our set S that we created, well, we can remove V sub 1 from that list of vectors, and the span of V sub 2 through V sub P is still going to be the same subspace H. So we have reduced the number of vectors in our set here to start to minimize the number of vectors I have to write down, but still get the same span. And you can continue this process as much as needed to get down to the bare minimum number of vectors that still span the same space, that still build all of H. And that's actually what part A is saying. If one of the vectors in our set of vectors here is a linear combination of the remaining vectors, well then, the set formed from S by removing the offending vector will still span H. That should be somewhat obvious to you. So let's suppose that we removed V sub 1, because it was a linear combination of all the previous vectors, and we take a look at V sub 2 through V sub P, and we find out, hey, wait a second, V sub 5 is a linear combination of all the other vectors. Well, you can remove that as well and still be able to span H. And if you continually do this, you'll arrive at a set of vectors that are linearly independent because you're removing the linear dependency every single step of the way. And eventually you'll have a bare minimum number of vectors that are linearly independent and still span your space. That resulting set of vectors will be a basis for your space. And that's where the second part comes in. Second part of this theorem says, hey, if H is not the zero vector, which it's likely not going to be, then some subset of our original collection of vectors has to be a basis of H. Remember, that original collection of vectors spans H. So some smaller subsection of those vectors, or it could be the same collection of vectors, but it might be a smaller collection of those vectors, should be the building blocks or the generating set for H. And that is a spanning set theorem. It's not a proof, but it's just a conversational justification that given a set of vectors that span a space, you can start pruning back those vectors until you get to the key vectors that will still build your space, but are now linearly independent. If you want to see a proof of this, it's in every single linear algebra textbook. And that leads us to our final concept, which I'm just being repetitive at this point because I've said it so many times, but it's good enough to state again. A basis is a spanning set that is as small as possible to retain linear independence and as large as needed so that you can span the space that you're considering. Now, I know this video is somewhat long, I apologize, but I hope it is helpful for you in your linear algebra course. I hope you have a wonderful day. Be a kind human being.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.